because I spent several years there teaching in German medium. So, and the German woman, my collaborator, Jutta Pons, is the woman physician, okay, working in gravity theory. She had very strong protests when they are not fair enough to women. So, anyway, so Noether's method, if you consider, for example, a complex scalar field theory or a spinor field theory, now just consider massless. So now this has a global symmetry and not a local symmetry. Through the Noether's procedure, you change your derivative d mu to covariant derivative, capital D mu, which is little d mu plus IE a mu. So you introduce a gauge field into the theory with the help of a covariant derivative. And then your gauge field, like a mu in quantum, in electrodynamics, is still non-dynamical because there is no kinetic energy term. So you add a kinetic energy by hand to your Lagrangian of the action of the theory. And then this theory will have local symmetry, local gauge symmetry. So this is well-known Noether's procedure of gauging a symmetry into a local symmetry. Now, I would like to apply this method also to my supersymmetric standard model. Okay. So, if I do that, I will have to take help of the so-called supercovariant derivative. Now, my gauge field will have to be a spin 3/2 field, not a mu, but a spin 3/2 field, which would be a gravitino. It would be a spinor vector or a vector spinor. Okay. By usual standard properties of the spinors and vectors. Okay. So you take help of the supercovariant derivative, and then you have to make the gauge field dynamical, which means you introduce its kinetic energy, and this is being given by so-called Rarita-Swinger model, Rarita-Swinger action, Rarita-Swinger term, and it was given in July 1941 actually. So you can imagine, 1941 it was written down by Rarita and Swinger, very famous. So here the gauge field, then you try to make it dynamical, you introduce a kinetic energy term for this gauge field, which is, so the kinetic energy of this field is given by Rarita-Swinger term in the action. But now, so graviton is there because you have introduced gravity, because you have made it local. As soon as you make your transformations local, symmetry to be a local gauge symmetry, gravity will automatically come. If there is a supersymmetry in the theory, gravity will automatically come in the theory. If you make the space flat, gravity will also run away, disappear. Okay? So, then you also have to give the kinetic energy to the graviton, and that is given by the Hilbert-Einstein term, Hilbert-Einstein term, capital R, expressed in terms of times appropriate. So Hilbert-Einstein action. And then one more thing remains to be done is that my metric tensor was flat in supersymmetric standard model. I have to make it also a field. So instead of theta mu, I write g mu, and this g mu I take it as a function of x mu, so that it varies, and each and every point of the space-time manifold is now dynamical. So this is called the general coordinate transformation. Okay, so the g mu of x mu, the metric tensor, is invariant throughout point to point in the space-time manifold, which is now a curved space-time manifold. It's very simple. I am not telling you any mathematical steps, no details, no frightening mathematics. Very simple idea. Whatever extent you can do or pursue, you don't have to actually do everything. For younger generation, this is my message. At least just play around with the things and ideas and concepts for it. Understand the curiosity of mind, for the curiosity of mind. Then you can give up. So you know, आपने एक बर्फी खाया, एक कटलेट खाया, चाय पिया, to give you an idea what a cutlet is like. Okay. So that is the idea. You don't have to fill your entire stomach with that. you still wait for the lunch or the dinner, right? So this kind of a theory, so you have supersymmetry in the theory, supersymmetric theory. Now you also have introduced the local asymmetry into the theory, and therefore gravity has automatically come. The only deficiency in my standard model and supersymmetric standard model was that it did not have gravity into it, and therefore it could not explain many things. Now, you want to look for a theory that would also take care of all these worries, including your singularities at Big Bang and everything. So that would be your, this theory is known by the name of supergravity. So that is why I put this word supergravity there. So in fact, supergravity theory might turn out to be this is the most promising candidate theory of the theory of quantum gravity. I would not say this is the final. I would take few more minutes to come to that point. So supergravity theory, now it depends on the also in supersymmetric standard model how many supersymmetry you introduce. What do I mean by that? How many transformation parameters are there? One or two or four. So that is the number of supersymmetries in the theory. Theory has to obey superpoint algebra and so on, some properties. So and also the supersymmetric transformations. All these things have to be verified. Fine. So in now after having done that, I would like to see what are the advantages if I take n equal to 1 supergravity theory. For example, let me skip some details of supersymmetric standard model. Let me just talk about supergravity. So for n equal to 1 supergravity, I would have one supercharge. I applied it on my +2 helicity state, which is a graviton. I could tell you the details if I had more time how to do it. Even in words without any mathematical calculation. So now, so there will be one graviton, one gravitino. But if you introduce two supersymmetries, n equal to 2, you will have one graviton, two gravitinos, and one vector field, electromagnetic vector field. Because one supercharge would annihilate it once, it reduces the spin by 1/2, and it can happen in two ways. So two gravitinos, if you apply both of them to the graviton state, so you subtract 1/2 and 1/2 from 2. So it will be spin one state, that is a vector photon. Had Einstein been alive today, this was his dream theory of unifying gravity with electromagnetism. And n equal to 2 supergravity theory does that. So you have one graviton, two gravitinos, and one photon. So you have unified this gravity with the electromagnetic force. Now let me not explain n equal to 4, let me go to n equal to 8 supergravity theory. I will have 8 supercharges. I can annihilate a graviton state in 8 different ways by Q1, Q2, Q3, Q8. I have 8 supercharges. So I will have 8 gravitino with spin plus 3/2. Then if you can annihilate it by 2 at a time, by 3 at a time, by 4 at a time. It is given by what we learn in school. 8C0, 8C1, 8C2, 8C3, 8C4, 8C5, 8C6, 8C7, 8C8. 8C8 would again be 1. 8C0 here 1. So 1, 8 gravitinos with spin plus 3/2. Then spin 3/2, then spin 1 vector particle, there would be 28. Then 56 particles would be for my friends of neutrino physics. There would be 56 spin 1/2 particles with spin plus 1/2. Then there would be 70 scalars with spin 0. So instead of 1 Higgs God particle, now I would have 70 God particles in my n equal to 8 supergravity theory. If I do it further, I would now have negative helicity states, which is perfectly allowed. So 1, 8, 28, 56, 70, then 56, 28, 8, and 1. So last one is graviton with spin -2. Last 8 are gravitinos with spin -3/2. then vector particles with spin minus 1. Okay, spin and helicity, I would explain how one obtains that. It's very simple. And 56 spin 1/2 particles, if they are massless, then they are neutrinos. If they are massive, then they are electron type. If they are massless, then they are neutrino type. So I think my friend, they usually the time not able to see, he must be hungry, young man. So he told me he was doing neutrino physics. So many people work on neutrino physics, and one has to, so this will have 56 new spin 1/2 particles, which is spin plus 1/2, 56 spin minus 1. And so on. So actually, n equal to 8 supergravity unifies all the 4 fundamental forces of nature. That is the conclusion of this theory. So, and then that is the best theory of quantum gravity of zero-dimensional particles and fields, which we talk in field theory in particles, conventional particles and fields. So, and one can write down all the Feynman. One can write down all the possible Feynman diagrams and calculate all these processes that the particle physicists do across the world. So you can do it also in n equal to 8 supergravity. If and when I have time, I could tell all the relevant Feynman diagrams and all, but they are calculable. They are doable. Their experimental signatures are very big, and therefore you need to look. You don't have to depend on SLAC, on SAR, electron matter, but you have to look for alternative experimental test verifications for them. That would be a kind of conclusion on supergravity theory. However,